Hello everyone and welcome to my Gaussian beginner series. If you are new to computational chemistry or you just started using Gaussian, this series is for you. Before we start running calculation, before we write input file, we need to understand something very important. What is chemical model? What is mathematical model? And what does model chemistry actually means? If you understand today's lecture, everything in Gaussian will start making sense. Let's begin from zero. So, first, why do we need models? In real life, we cannot see atoms directly. We cannot see electrons moving around a nucleus, but chemistry studies atoms and molecules. So, how do we understand something we cannot see? We build molecule. A chemical model is a simplified representation of a real chemical system. For example, in the screen, you can see ball and stick model, wireframe model of a ethane molecule. These are not the real molecule. These are the simplified pictures that help us understand bonding and the geometry. This is very important concept. A model is not reality. This is the approximation of reality. Why? Because the real systems are too complex. So when we look at a simple molecular model such as ball and stick model, we gain a physical understanding of the molecule. We can visualize its shapes, approximate size, and whether the part of the molecule can rotate or transform into different conformation. We can also estimate whether two functional groups are close to each other or far apart, and whether a particular region of the molecule is accessible for a reaction with other molecule. However, this is the model you see on the screen. These are the simplified model. It does not represent how molecule actually behave at the quantum level. For example, it does not provide direct information about the bond strength or electronic structure. Even though it is simple and not perfectly accurate, it is still very useful. For certain properties, it works well as a practical tool. Next, similarly, we can think about mathematical model. Consider the ideal gas equation. Real gases do not behave ideally at all room temperature and pressures. At high temperature or very low temperature, real gases deviate from ideal behavior. However, within a certain range of conditions, the ideal gas equation provides a very good approximation. So, even a simple model can be extremely useful within the appropriate limit. So, in computational chemistry, we work with different level of approximation. Not every computational model method will be perfectly accurate for every property. Some methods are more accurate but require more computational time and resources. Even though we want to always use the most accurate method, that is not always practical or feasible. We must choose a method that provides a sufficient accuracy within the time and computational resources available. We can compare computational work to a laboratory work. In the laboratory, before performing a reaction, you prepare the reagent, select appropriate condition, and design the experiment carefully. Similarly, in computational chemistry, we must identify the species we want to study, determine which properties are we interested in, choose the appropriate level of theory, build the molecular structure, run calculations, analyze the results carefully. Only after these steps we can interpret the results and connect them to our original research questions. So the next we will see some interface of the Gaussian. So this is the Gauss view 6.1.1, and now we will see some of the tools available in toolbar. Here this is the file option where you can see open new files, see your old files, save, and many more options. Then next is edit and then tools. We will learn more about these tools one by one. But first, we will talk about our lecture that we studied, model, chemical model. Here in this screen, you can see I create ethane, C2H6. The big dark gray balls are carbon with three hydrogens attached to one carbon and the same three hydrogen attached to another carbon atom. This is the input file of our structure DJF, and you got the same uh, after optimization output file .log file, and you see it takes 5 steps to complete optimization and frequency. I run optimization plus frequency calculation. This is how our input and output file looks in Gaussian. Then in the next lecture, we will learn how to create the input file and how to set the parameters in input files. And we can see our output file in the form of text file. Here there are so many information. We will analyze the information one by one. This is just the overview of how our files looks in Gaussian. So let's talk about our chemical models. By clicking this option, you can create a new input GJF file. When you click, a new window opens, and if you want to create some molecule, let's suppose we will create the same one. For example, I want to create carbon tetrahedral. This I open this periodic table and select the carbon tetrahedral. It shows me in this screen. Now I'm just by clicking anywhere in this screen, you can create the same molecule. Here you see this is CH4, and I want to make a ethane. So I will replace this carbon hydrogen with another carbon tetrahedral. So this is our carbon ethane C2H6. This is the ball and stick model. We can visualize this in different orientations. We can click by labels to show the one to show the number of atoms and which atom is in which place. And again, by going to view, you can check the labels, like this is carbon 1, this is carbon 5, and these are the hydrogen attached to these carbons. And next, going to display format, you can change the background of your input screen. Let's suppose I will change it to black. So now it looks more clear. Here are so many options. You can also customize according to your choice. Next, quality. And here is a high layer ball and bond. You can change to tube, model, and ball and stick, ball and bond, wireframe, and you can also choose no. And you can select different molecules with different orientations. And the next text size, you can increase and decrease the text size. Like if I want to more larger. That is again back to. You can also change the color. And next is the surface. So this is how our atoms chemical model looks in our Gauss view 6.1.1. And here this is the calculate button. From this option we can set our Gaussian calculation input file settings. Automatically it shows me Hartree-Fock 321G geometry and connectivity keywords, but you can set according to your requirement. In this lecture, we will only see chemical model and how our Gaussian look like. So there are so many options. Like if you want to calculate the single point energy, you should select this. If you want to optimize your structure, you should choose this one. If you check your frequencies, if you want to check if there is any imaginary frequency in your system, you can also choose this one. If you want to do optimization plus frequency, you can check this one. If you want to do an IRC scan stability and NMR of your structure, you can also choose this one. For example, if you want to only do optimization, and again you can see for every option here a different interface will appear, and we will study all these points in our next lectures. And for example, for optimization, just for now we see optimize to a minimum, and TS transition state, and these are also for some transition state, but for now we want to do optimize to a minimum and keep all these as default. And then this is the method we are talking about, and we choose ground state, TFT, and there are many options available for different theories. Like I choose the B3LYP basis sets. There are many options available for, let's suppose for we choose for this G31G and charge zero singlet and empirical dispersion default. And I will not change any settings here because we just want to see job title. You can see, you can write optimization plus frequency calculations, link zero. I'm using the cluster system, so I can assign it to highest memory 100 GB and share processor like 15. If you are using cluster or your Mac or laptop, you should choose according to your system. And here you can specify the number of CPUs you want to choose. Let's suppose for now I want to finish the calculation fast, so I will choose T2 95 just for see how Gaussian works. And there are so many options for now. We skip this one and default, and you can see your input file here. This is the number of processor. We choose 15, memory, checkpoint file, CPU, number of CPUs, and this is important. root section. We are doing optimization. Our 3D is B3LYP, basis set, and geometric connectivity. We are doing the optimization plus frequency. This is our charge, this is our multiplicity, and these are the coordinates. So just submit. It will ask save. You can save anywhere you want. For example, I save here C2H6 OPT array optimization plus frequency and then save. So it will ask about do you want to submit your job and will I notify when job is finished? So check this if you want, and if you don't want the notification when job is finished, you can uncheck this one. If I check this one, yes. So after maybe 1 hour 2 minutes, maybe not 1 hour 2 seconds, take only. You can see checkpoint file and the log file. Log file is our output file, and we will learn about checkpoint file. So I want to see how my log file looks like. So I will open my log file. So it takes 4 optimization steps to reach its lower ground state. So you can see the structure. You can also zoom in and zoom out by just use of you can log in, you can rotate and by holding a shift and arrow button you can move up, down, and you can rotate in 3D. So this is all about our today's lecture. We learn about model chemistry, mathematical equations, and the what. So this is all about our today's lecture. We learn about what is a chemical model, what is a molecular model, and what is mathematical model, and what is model chemistry, and how we see input files in course view, and how to make a simple molecule, and we see its different chemical models, ball and stick, wire model, tube model, and how to submit the job on a Gaussian. On the coming lecture, we will learn more about our Gaussian. If you like, please subscribe and follow for more.